Hello, this video is going to be on how the ALU works. It's part of the processor and it fits in with everything else as shown on this slide. You've got the control section here, the RAM here, and the ALU here. And effectively, according to what operation the control section tells the ALU to do, it will perform various arithmetic or logical or operations on it. The ALU is the arithmetic logic unit, if I've not already said that. So what it does, it takes these two inputs A and B and it performs either arithmetic or logical operations on them and then outputs them down the bottom here. And the control section can send either R0 to A, say, or R1 to B via these bits and pieces here. But the main two inputs are these two, and the main output here is down the bottom. Then it's got all these bytes, bits. These are bits, not bytes, down the side, which are also important. Okay, so we'll go through that in more detail now. So as I was just saying, what comes in here is effectively the operation. You can see we've got effectively 7 operations that this ALU can do. Okay, and this bit here selects those. Now there's 3 bits, so what's going to come in, if it's a bit that comes in, then the first bit can be one of 2 things. Okay, the second bit can be one of 2 things, and the final bit. So how many options do we get altogether? Okay, well we get 8, and that's just going to be, remember back to before, the what allows us to do that is just the 8x3 decoder. Okay, and we'll see that in action in a later slide, but it does make sense. There are 3 bits, 7 options. How can we get them all 2x2x2? That's how that works. Remember the 3x8 decoders we did in the RAM? I think they wrote them like that, don't they, as blocks. 3x8, 3 bits go in, 8 effective options that you can select. Okay, these other ones, these carry in and the carry out, they're together, they're both used. They can be used by the shifter, but they're definitely used by the adder. And if you imagine doing column addition, it's very much like that. Okay, you can carry something in and then it's put in with the column addition. And if you get 2 big numbers that you're adding together, you might want to imagine these 2 you're adding together, and they go over the magic 2 to the 8, then you're going to want to carry out as well. Okay, these bits here, they're not sort of part directly of these 7 operations really. They're put in with the exclusive OR, and they're called comparators. So basically, this bit will be on if A is larger than B. This bit will be on if they're equal. Okay, this bit will be on, I think, if the output here is 0, but we'll see that for definite with the final slide. Okay, so you won't be left in any confusion. And that's what these other bits do. So that's the whole sort of top level understanding of the whole unit. So we're going to drill down again as to how basically each of these operations are performed now. Okay, so some of them are very simple, and we'll do this very quickly. Excuse me. Well, the shifter is very straightforward. It literally just, I'm not going to spend a huge amount of time on this. It just shifts everything. This is a right shift. So this coming in here is effectively would be our A. What comes out here would be down the bottom here. Okay. If there's just one, this shifter works on 1 byte. If it does work on 1 byte, it's always on the A byte. This shifting operation works on 1 byte. It will always be the A byte. It's going to come in. It's going to shift everything one way. Now, this shift in can come from the carry in, and this shift out can go to the carry out. Okay. The R1 is always going to be basically the A, and the R2 is always going to be the output down here. They just register 1, 2. Okay, we've used A and ACC, C down here. No, ACC. Yeah, so that's how that works. The other way this can work is this shift out can be moved to shift in, so there's no carry out or carry in at all, and the whole thing just wraps around that way. So that's how the shifter works. Now, one thing I do want to explain is that this effectively can do multiplication, because if you think about decimal numbers and how they work, okay? Well, if you want to do, let's say, 31 times 10, all you do is you move everything one place over, so it would be 310. Now the same works in binary. If you want to do, let's take a binary number, okay, 0, 0, 0, I'll do it as a bit long-winded this, but there we go. Okay, so I take that number. Well, what is that? That's going to be 1, no 1s, 2, it's going to be 6. You want to multiply that by 2 now. what it'll effectively do is it'll shift them all one way over. So now I need how many zeros? I need 4 zeros, 2 ones, 2 zeros, okay? And you can check what this is, okay? What is it now? It should be 12, shouldn't it? So if we look across, well, no ones, no twos, we've got a 4, and we've got an 8, so we get a 12. And here, what do we have? We had a 2 and a 4, which gave us a 6. So you can see what we've effectively done is timesing by 2. So although this, it's only timesing by 2, but of course you can imagine how timesing by 4 would work, and you can imagine how timesing by 8 would work. So it's not too big a step to imagine how you might use this shifter to effectively enable the computer to multiply by other numbers. Okay, so we'll move on from the shifter. Okay, so we've got the knotter now. This really is very straightforward. All the knotter does, it's AC here, see? So we're taking in the A here, we're going down to the C here. All it does is take the input and change it. So if the first one's a 1, remember these are all bits now because we've broken down the byte into its 8 bits. That's what's happening here. Excuse me again. If this is a 1, well, what will come out here will be a 0. Okay, if this is a 0, what will come out here will be a 1. It basically just knots the entire set of inputs. It's a very straightforward operation, and that's all it is. Okay, some of them are quite straightforward, and we'll skip over those quite quickly. And the ANDer, again, it's equally straightforward. All the ANDer does is it takes A, the first A, it takes the first B. It looks a bit complicated, but that's fine. And if they're both 1, well, the output will be 1. Because that's how AND works. If they're both on, the output's on. However, if there's a mixture, so there's 0, 1, or they're both zeros, then the output will be 0. So it's just applying for each bit in the byte. It's just ANDing each bit and then putting the output back to another bit, and that bit's C. So again, that's pretty straightforward how that works. Okay, the ORA. Again, this is also a very simple one, so I won't spend a huge amount of time. I think you can see all that's happening there is that I'm ORing the A with another A. So, well, what's going to happen? Well, if they're both 1, clearly they'll be on, because that's how the OR, it's not an exclusive OR this, it's just a normal OR. So both on is on. Either one of them on, so if it's 1, 0 or 0, 1, that will be on, and if they're both off, that'll be off. Okay, so it just applies what you already know about an OR to each of the 2 bits there, and that's that. Okay, the exclusive OR works, again, almost exactly the same way. Okay, there's more to be said about this though, so because of the comparators, remember I mentioned right at the start. So exclusive OR, just to recap, if it's 1 and 1, that will in fact go to 0. So if those are both 1, you get a 0. Exclusive OR means it's sort of exclusive in the sense you can't have both being on. Okay, it's one or the other. Exclusive just means one's on. All right. I don't quite know why they use that word, but it's the way it is. All right. So we'll go a little bit further with this because there is some more complicated stuff with the exclusive OR. So this is the comparator and the 0. Now, this does get a little more complicated, so this is a bit to really listen into. I found this quite tricky the first time I did it. Now, the way I tend to think about this is, imagine I've got, this is my A and my B here, but I'm going to represent them as a byte. So it's 8 blobs, so I can talk about them together if you like. And I do the same for B. Okay, I've got 8 blobs. They're not zeros, these are blobs. Okay, let me fill them in so it doesn't get confusing. Alright, they're not zeros. But that's my A, and that's my B. And for the comparator here, this isn't, the adder is a similar sort of thing, but the adder will start at the bottom. But for the comparator here, we want to start at the biggest number in the byte. So we're going to start here. And again, these are bits, so it's looking initially at these 2 bits. And the assumption about them all being equal is to start with, because this effectively feeds down, okay? All bits above are equal. If I'm here, well, if this is set to 1, then that means that, and I'm here, say now, okay, we'll talk about moving to the top again in a moment. It means that all of these are equal, alright? So if I'm here, then all of these are equal. That's equal to that, that's equal to that. Okay? If I'm here, that's equal to that. If I'm at the start, then I need to start this off. So I'm at the start, then that comes in as a 1. Okay, here, and again, this, you see the bits above equal, bits above, and this again works in a all bits above are equal. Well, this means that A has been found to be larger from above. Okay, and we kickstart that with a 0. Right? So that all bits above are equal, we assume that to be initially true until we find a condition. If you think about stepping through this, how could you do it? So you could say, well, are these two equal? I'm going to assume they're all equal. Are these two equal? Well, yes, then I can say they're still equal, can't I? Are these two equal? Yes. Are these two equal? Yes. And you would keep going, okay, until you found where they weren't equal, and then that gets set to false, okay, but by this logic here, and then that ripples down, and so that it's never going to found to be equal again. Effectively, as soon as you found one where they're not equal, you perpetuate that signal down the chain. Similarly with A larger, if we assume that A is not larger to begin with, okay, well, what will happen if they're both the same? Okay, then it's a similar sort of logic. It just passes down from one to the other. So anyway, for now we'll start that's 0 to begin with, and we'll look at how this works. So how does this work? All right. Well, if A is, let's have a think about this bit here. So this unequal here makes sense because this is an exclusive OR. So if they're different, then this will be 1. If they're the same, then this will be 0. So you see this output here has been, the unequal output has been threaded through a NOT gate which turns it to equal, right? Now this bit here is fine as well because all bits above are equal. So what we found out is these two bits are equal. Well, if all the bits above are equal, then I'll continue to be equal. However, if either one of these conditions is not met, either this is not equal or all the bits above are not equal, then we pass on that they're not equal, and that will come into the next one. So what you'll effectively get at the bottom when you move the whole chain is, well, if they are all equal, that will be a 1. Okay, the final bit that comes out of the whole thing. Okay, out of the whole ALU. If we ripple down the chain and we found them all to be equal, it will still be equal at the bottom. Okay, so let's have a look at the A larger. Well, we don't assume A is larger than B to begin with, so we put a 0 there. Okay. Now the next thing we get here, all bits above, let's say A is larger, so this will come in, it's going to assume to be false. Alright, now there's an AND gate with 3 ANDs here, so either A is larger because it's been found to be larger above, or, right, the other way this can happen is A can be larger if it's found to be larger now. So that would mean, okay, that they must be unequal, that's one AND. A must be 1 and B must be 0, that's the other AND if you like, and all the other bits above have to be equal. Alright, if all the other bits above are not equal, you cannot say that A is larger, because it could be that above somewhere there's a bit above this, so wherever we are in this byte, at some point above we will have B as being larger than A, right? Okay, so that's going to go into that AND there. We've got A's on, we've got the unequal is on, and all the other bits above are equal. If that is the case, then we can say that A is larger, okay, and it goes down. In no other situation can we say that, okay? And this will change then, won't it? Because we've got this 1 will come here, that might be a 0, but that's fine. That then gets changed to a 1, alright? Otherwise it will just remain at being 0. Good. So I think that does explain how they both work. I hope that's clear. It's well worth just looking at that diagram a few times just to make sure you complete it correctly, because it is a bit tricky. Okay, but that's basically it. If you go on to the next one, then all I'm doing here really just tying up a few things. We're tying up basically, you see that all together now. What I was saying about rippling down, okay, it starts off as being assumed, A starts off as being assumed equal. If it's found equal on that byte, that byte, that byte, that byte. I could draw the diagram out again, I'm not going to. 0 if A is larger, it tests if A is larger at each one in the way just described, and the A larger, the equal, they map to this bit that comes out the whole unit. Alright, the bus in 0 here. Good, so that's again, that's applied to the actual output here, which I'll show you again on the last slide. So, I haven't really explained how that works, have I? I should explain how the 0 works, right? So the 0 bit here, well, if you imagine this is a big OR, so for this to be on, the minimum criterion, if you like, is at least one of these is on, right? And that will be a 1, that will output a 0. So 0 outputting a 0 means that the output is not 0, right? You get a 1, okay, when all of these are 0, Therefore, and that's the only way that the output here can be 0, and then you get a 1, which is a little bit confusing, isn't it? But basically, let me write this down. If you follow that, what I've said through, okay, 0, this bit here, if I can write clearly enough, which is doubtful, 0 equals 1 implies that this here, what goes into the bus, is all zeros, which is a kind of confusing logic, but you know, learn to live with it. It's not the end of the world, right? They're all zeros. If any one of them, let's say if this one's a 1, let's just cross it out and I'll make that a 1, well then the output here will be 1, the output here will be 0. If they're all 0, then the output here will be 0, and the output here will be 1. Alright? So that's a tricky one, but you know, you can get there, I'm sure. Let's delete all of that, take pause off, on to the next thing we're going to do. So now we've got the adder. Now I've missed the carry in out to begin with, because just to simplify things a little bit. Alright? And again, this is working on bits. This time, however, if I draw the diagram I had before, those bits, it's going to be they're going to work the other way around. They're going to start at the bottom of the byte and move up. Alright? So rather than as last time, I've got 7, haven't I? So another 2. Rather than as last time we started here, now we're going to start here, right? Now, let's have a think about what we would want to happen, and then we'll explain how this works. If these two are the same, and it's just like you can add bytes, just like doing column addition with decimals, you can do that with binary numbers. It's no big problem. So let's say they're both 0. What do we want to happen? Well, 0, 0. Well, that adds to 0, and also we wouldn't want to carry anything. So I'm going to put my carries to the left rather than down below what I did before, because it makes it a little bit simpler, and I'm only going to add 2 numbers like this. I'm not going to add a whole load across like you would have done at school. So I want the actual sum to be 0, which is this one. I also don't want to carry anything. What's going to happen if I want 1, 0, 0, 1? Well, that's going to be more or less the same. What do I want in both of those situations is I want 1, but I want to carry nothing. So the sum's 1, I want to carry nothing. Here the sum's 1, I want to carry nothing. What happens if I do 1 and 1? Here the sum's 1, I want to carry 1, right? Because, well, I get 2, don't I? Okay, so 1 plus 1 means I get a sum of 1, and I want to carry 1. Okay, I hope that makes sense. Good. So no, it doesn't mean that, does it? Ooh, 1 plus 1 means, oh, I made such a mistake. 1 plus 1 means I want to get a 0 here, doesn't it? Sorry, I apologise. So if 1 plus 1, then it's like going to 10. You put a 0 here and you get 1 over because you go to 2. And that gives you what you'd expect. Okay, sorry about that. So you get 1 plus 1. Doesn't give us a 1 here. That's not what we want. Effectively, 1 plus 1 is 2. So that goes into the 2 column there. Okay? Good. 0, 0 is a 1, and all the rest makes sense. Good. So let's now have a look and check that these work here. So, well, 0, 0 goes into, it's an exclusive OR. 2 zeros give us a sum of 0. Alright? Well, this is an AND, so the AND is the carry bit, the bit on the left. Remember, it's always some carry, some carry. Okay, these 2 bits go into the AND gate, and they're both 0, so you get a carry out of 0. Alright? I think it's pretty clear how these 2 work, okay? Because exclusive OR will clearly be on, so the sum will be on. We'll get a 1 here, and we'll put these 2 together, 1 and a 0, you're going to get a carry of 0, okay, for both those 2. Here we get a 1 and a 1, put those 2 together in exclusive OR, you're going to get a 1 out, okay, you get a 1 and a, well, no, because it's an exclusive OR, you don't get a 1 out, I'm saying doing it again, you get a 1 and a 1, the exclusive OR will go to 0 for the output, and the 1 and the 1 here will make the carry of 1, because that goes into an AND gate, okay, yeah, so that's that covered. Let's clear that and then we'll move on. Okay, so this is how it works fully, okay, with the carry in, the carry out, and everything else. So, well, we've got to carry in, and the first thing to check, that makes it life nice and easy, is that if the carry in is equal to 0, we should get the same as we had before. So let's Let's write those sums out again. I think that's worth doing. So we're going to have 0, 0 is going to go to 0 with 0 carry. 1, 0 is going to go to 1 with 0 carry. 0, 1 is going to go to 0, 1 with 0 carry. 1, 1 is going to go to 1, 0 with 0 carry, right? So if there's no carry in, it should be the same as before. So the first thing to probably check is that if I put this carry in equal to 0, does this whole system now with the carry in and the carry out work as it did before? Well, I think it's pretty clear that it does, because if you put a 0 into here, the only way this sum can be on is if this exclusive OR here is on. So if a 0 goes down here, it's like this exclusive OR isn't here, alright, because this is on all the way along, and that's on only if the A is on, right? Because if that's 0, it's the only way that the exclusive OR can ever be on. So that effectively means that this exclusive OR is effectively not there if the carry in is equal to 0. Similarly, if I put a carry in 0 here, well, this AND will always be off because it's an AND, alright? So that's effectively not there, that's effectively not there, it's like it just flows through there. Here it's like it just always outputs 0, and it's going to an OR, so you can see what's going to happen next. So the only things that are left are this AND gate here, which will be on, only if they're both on, which is exactly what it was before. Now this output will always be 0, so the carry out will effectively be 1 when the when A and B are both on, okay? Because again, like this one always outputs 0 now, so the only way this can possibly be on is if this input's on, alright? So that does work in exactly the same way as before. Now if I turn the carry in to be 1, what do these two now become? Well, this one's going to become a 0 and a 1. This one's going to become 1 and a 0, because you're adding 1, you move it over. That will be a 1 and a 0, okay? If you imagine adding 1 to each of these, what's going to happen? Well, that's 1, it's now going to go to 2. That's 1, it's now going to go to 2. That's 2, it's now going to go to 3, okay? So this is what we should get when the carry in now, that's a carry in of 0. So the in there is 0. This is if we have a carry in of 1. So we need to check this. Well, if they're both 0, this is reasonably straightforward because this will be 0. However, the carry in will be 1. So the output, if they're both 0, the output here will be 0. So what goes into here will be 0. However, the carry in is on, so the sum will be 1. So that makes sense with that. The carry out, will the carry out be 0? Well, clearly if they're both 0, they're both 0 going into here, so the output of this one's 0. Well, if this carry on is 1, that will go in as 1. This output will be 0. What comes out of here will be 0. Okay, so we're now going to get a 0 here, a 0 here. The carry out here will be 0. Alright, so next one then. Again, we've got carry in as being 1 now. We'll just indicate, I'll put a 1 here, probably make it a bit simpler. And we're going to check that this one works. Well, what's going to come with our sum? Our sum now, this will be on, okay, but this will also be on. It's an exclusive OR, so the sum will be off. Okay, if these are different, then this is on. But now these are the same, so this turns off, right? Good. Similarly, we've got a carry in going on here. Goes into this AND gate. Well, that might be on, but this is most definitely off, so that goes to 0. This is also off because they're different, so the carry out 0. And I think it's pretty easy to see that that logic actually encompasses both of these. Okay, so you don't have to think about A being 1, B being 0, then A being 0, B being 1 as different cases. Just think of them as the same, because it's actually invariant. If I change this around, A and B around, it makes absolutely no difference at all to the system. So now let's think about A and B both being 1. Alright, well, the output of this will be 0. Okay, because it's an exclusive OR. If they're both on, the output's off. The carry in is 1, so the sum is 1, because there's 1 and 0 there. Okay, the carry in is 1 here, so that goes to 1 there. However, if we look at this one, in actual fact, the carry out here, well, they're both on, so that would be off. So actually, the output here would be 0, right? But if A and B are both on, right? Well, what happens if A and B are both on? You come into the AND, this will turn on. This is an OR, so the carry out will go to 1. So you get exactly what you'd expect. And the sort of abbreviation for this system is this here, okay, and that's just all of this stuff, if I wrap it up properly, put into that box there. Alright, so you don't have to, every time you write it, you draw this gates down, but now you know exactly how it works, okay. So that's quite tricky, but it's quite nifty as well, because there you see, you fully understand how addition's done. Let's move on to the next one. Okay, and this is just showing it in context, all that you really actually do. Okay, you carry in, you do it, difficult to see this, you do it for the lowest bit. You can see the bits are actually starting at the other end now. So you do it for the lowest bit first. There's the lowest B, follow that one back, you can see it's the lowest A. Carry in, the carry out from that goes to the next one. Okay, and the next one, and the next one, and the next one, and the next one, and so on, then you get a carry out. And that's your sum, that's your C at the bottom. So that's how addition works. Again, it's a similar sort of rippling idea. Let's go on to the next bit. Okay, so finally, this is how it all ties in together. So here you've got the op goes in, it goes into this decoder. So let's say I pick, I want to do the first one or something, then you got 8 options. One of those are binary options, one of those selections of 8 will go to nothing. Okay, another one will turn just this one on, and all of these will be 0, right? So all of those will be off, so you'll only get the output from the XOR say, right? And that's basically how it works. I mean, let's have a look, follow these enabled gates around here. All this enabled thing is doing is basically saying, okay, if I want to stop output, I'll turn this off. You're turning this block off here, which effectively just zeros everything that comes out of here, so it doesn't have any impact. So if this is 0 here, or you just and the output with 0, and you'll get a 0. So that's how you select that. That's no big deal. There are a few other little bits like the carry ins and the carry outs. If you get a carry in, so you see the carry in goes to the shift, it goes to the shift left, shift right. It also goes to the, I didn't explain both of them, but I think you can imagine how they both work. It also goes to the add. Well, and also to make it sure that we get the right carry out. Well, again, it's moved to the decoder, isn't it? So if you select one, you can only ever select one of these wires at one time, because that's how a decoder works. So if you select this one, if you turn this one on, all the others will be off, right? You get a carry out here, right? This 0 here works in the same way as before, right? And again, it does apply to the output, doesn't it? You can see it quite clearly now, because it's on the same route as this here, yeah? So that's basically how your adder works, your ALU works, okay? Thanks for listening.